Welcome to Sleepy Stories, a calm space where learning and rest can happen together. Each story here explains how the universe works, using a quiet pace that helps your mind slow down. You do not have to stay alert or take notes, simply listen. If sleep does not come immediately, that is perfectly fine. The story will keep moving gently until your thoughts begin to settle. If these sessions help you relax or learn, you can support us by liking or subscribing. It allows us to continue producing new stories that mix curiosity with calm understanding. Tonight's subject is one of the most precise natural systems ever found, the pulsar. A pulsar is the dense, rotating core left behind when a massive star ends its life in a powerful explosion. The remaining object is small, about 20 kilometers across, but it contains more mass than the Sun. As it spins, it emits beams of electromagnetic radiation from its magnetic poles. When those beams sweep across Earth, radio telescopes detect brief flashes of energy at perfectly regular intervals. To scientists, those repeating pulses are a sign of extraordinary stability, making pulsars what many call nature's cosmic clocks. Before we reach the details of how they work, it helps to understand how a star can produce such an object. Stars begin in large clouds of gas and dust. Under gravity, these clouds collapse and heat up until nuclear fusion starts in the core. Fusion converts hydrogen into helium, releasing energy that balances the inward pull of gravity. The more massive a star is, the faster it burns its fuel. While a star like our Sun can live for billions of years, a giant star may exhaust its supply in only a few million. When that fuel runs out, gravity wins. The outer layers collapse inward, and then rebound in a massive explosion known as a supernova. The explosion throws most of the star's material into space, but the core remains. If the original star was extremely massive, the core becomes a black hole. If it was slightly smaller, it becomes a neutron star, a compact object made almost entirely of neutrons. This neutron star is what we later observe as a pulsar, if its rotation and magnetic field are oriented so that its beams point toward Earth. Detecting a pulsar requires sensitive radio telescopes. These instruments collect faint radio waves from space and convert them into electronic signals. When scientists first found pulsars in the late 1960s, they noticed that the signals arrived in an astonishingly regular rhythm, sometimes hundreds of pulses per second. Early researchers even considered the possibility of an artificial source before realizing that nature itself had created these signals. The discovery confirmed that neutron stars were real and provided the first evidence of matter compressed beyond atomic structure. Modern observatories continue to monitor hundreds of pulsars across the sky. Some rotate slowly, sending a pulse every few seconds. Others complete hundreds of rotations each second. The timing is so consistent that astronomers use pulsars as reference points to measure time, distance, and even the gravitational ripples predicted by Einstein's theory of relativity. A few pulsars are stable enough to rival the best atomic clocks on Earth, drifting by less than a microsecond in years of observation. Studying pulsars has given scientists valuable tools. By analyzing slight variations in their timing, researchers can detect unseen companions, measure the density of interstellar gas, and test physical theories under extreme conditions. The signals also have practical applications. Space agencies have begun experimenting with navigation systems that use pulsars in place of satellites, allowing spacecraft to determine their position anywhere in the galaxy. In this story, we will move through the life of these cosmic clocks step by step. First, we will look at how massive stars form and die, creating neutron stars. Then, we will explore the physics that makes them spin and shine so predictably. We will revisit their discovery, see how they are used in modern research, and reflect on what their precision tells us about the universe and about time itself. There is no need to remember every number or definition. The aim is simply to understand that even in the vastness of space, order exists. Stars live, collapse, and continue in a new form that measures time more precisely than any instrument humans have built. As you listen, allow these ideas to unfold at their natural rhythm. Steady, clear, and continuous. Somewhere between thought and rest, the pattern of these stars may help your own thoughts slow into their own quiet rhythm. Every pulsar begins its story as an ordinary star. The difference lies mainly in size. A star at least 8 times more massive than our Sun will not end its life quietly. Its weight determines its temperature, its brightness, and the pace at which it burns through fuel. The greater the mass, the faster fusion proceeds. Energy pushes outward, gravity pulls inward, and for most of the star's life those two forces remain in balance. Inside the core, hydrogen atoms fuse into helium, releasing enormous amounts of energy in the form of light and heat. This outward pressure supports the star's outer layers for millions of years. But hydrogen is finite. When it is gone, fusion must rely on heavier elements such as helium, carbon, and oxygen. Each stage of fusion requires higher temperatures and produces energy for a shorter time. The layers of the star become like an onion, each shell fusing a different element as the core grows hotter and denser. Eventually, the star begins to fuse silicon into iron. At that point, the process stops producing usable energy. Iron cannot release energy through fusion, it only absorbs it. With no outward pressure left to balance gravity, the core collapses in less than a second. The atoms are crushed so tightly that electrons and protons merge into neutrons, forming a dense ball of nuclear matter. The outer layers crash inward, rebound, and explode into space. This is a supernova, one of the most energetic events known in nature. The explosion releases more energy in a few seconds than our Sun will emit over its entire lifetime. It sends shockwaves through surrounding space, scattering the elements the star created, carbon, calcium, iron, into the interstellar medium. These materials will later form new stars, planets, and even living organisms. In that sense, a star's death is also an act of renewal. It seeds the universe with the ingredients for future systems. At the center of the expanding debris, something extraordinary remains. The collapsed core, now only about 20 kilometers across, spins faster as it shrinks, much like a figure skater pulling in her arms. It retains the original star's magnetic field, compressed to immense strength. If the remaining mass is below roughly 3 solar masses, the collapse stops there. The result is a neutron star, a body so dense that a teaspoon of its material would weigh billions of tons. If the core is heavier still, gravity overwhelms all resistance, and it becomes a black hole. For those that stabilize as neutron stars, the intense spin and magnetic field generate powerful beams of radiation from the magnetic poles. As the star rotates, those beams sweep through space. If one of them crosses Earth, radio telescopes register a repeating pulse. This is the origin of a pulsar. Its heartbeat, measured in milliseconds or seconds, marks the final transformation of a massive star from brilliance to precision. Understanding this process helps scientists connect the stages of stellar evolution into one continuous cycle. A cloud of gas becomes a star. A star forges heavier elements. The star collapses, creating a neutron star or black hole, and the matter it sheds forms new stars once again. The universe recycles its material endlessly, governed by physics that are simple in principle yet extraordinary in scale. For now, imagine that collapsed core left behind after the supernova. It no longer shines by fusion, yet it continues to emit energy through its motion and magnetism. It spins rapidly, perhaps hundreds of times each second, invisible to the eye but detectable to instruments tuned to radio waves. In the next part of our story, we will look more closely at that moment, the instant when gravity and motion create one of the most remarkable objects in the cosmos. The final seconds of a massive star's life are among the most dramatic events in the universe. For millions of years, fusion reactions in the core have held gravity at bay. But once the core begins to produce iron, energy generation stops. The balance that sustained the star suddenly disappears, and gravity acts without resistance. In less than a second, the core collapses inward at a quarter of the speed of light. Temperatures rise to over 10 billion degrees, and matter is compressed into a form unlike anything on Earth. As the core contracts, the infalling material slams into it and rebounds outward. This impact sends a shock wave racing through the star's outer layers. At the same time, a flood of neutrinos, tiny particles that rarely interact with matter, bursts outward from the collapsing core, carrying away immense energy. These neutrinos help drive the explosion that follows. The result is a supernova, an expanding cloud of glowing gas and radiation that can briefly outshine an entire galaxy. For a short period, the dying star becomes one of the brightest objects in the universe. The blast expels material at thousands of kilometers per second, spreading heavy elements like carbon, oxygen, and iron into interstellar space. These elements mix with surrounding gas clouds, eventually forming new stars and planets. Everything we are made of, our bones, our blood, the iron in our cells, was once created in stars that ended in such explosions. The universe continually rebuilds itself from its own remnants. At the heart of the supernova, the collapse leaves behind a dense remnant, a neutron star. Its gravity is so intense that atoms cannot survive as separate structures. Protons and electrons are crushed together, forming neutrons. The entire object is roughly 20 kilometers wide but contains more mass than the Sun. To put that into perspective, a single teaspoon of neutron star material would weigh billions of tons on Earth. This is matter at the edge of physical possibility, where quantum mechanics and gravity meet. The newly formed neutron star spins rapidly, conserving the angular momentum of the original star. It may rotate dozens or even hundreds of times each second. Its magnetic field, already immense in the parent star, is now concentrated to extreme intensity, trillions of times stronger than Earth's. These two features, rotation and magnetism, will soon combine to create one of the most stable and measurable signals in the universe. The pulse of a pulsar. The shockwave of the supernova eventually fades. The glowing debris cools and expands, forming a nebula visible for thousands of years. Within that cloud, the small, dense core continues to spin, invisible to the human eye but sending out beams of radiation across the electromagnetic spectrum. This is the beginning of the pulsar phase, the transition from chaos to regularity, from destruction to precision. Scientists studying supernovae often describe them as both endings and beginnings. They mark the death of a star, but they also forge the conditions for new generations of celestial objects. Without them, the universe would contain only hydrogen and helium. The diversity of elements, planets, and living organisms all trace back to these colossal explosions. In astronomical terms, a supernova happens quickly, but its consequences last for billions of years. Each explosion leaves behind both matter and information, signals that can be detected long after the light has faded. Among these signals are the pulses of neutron stars, which continue to reveal the universe's inner workings long after the parent star has vanished. In the next segment, we will look closely at what remains at the center of that explosion and how it becomes one of the most remarkable clocks ever discovered. When the outer layers of a star are blown away by a supernova, what remains is a small, incredibly dense core, the neutron star. It is one of the most extreme forms of matter in the known universe. Although it is only about 20 kilometers across, it contains more mass than the Sun. Its gravity is so strong that if you could stand on its surface, something no material could survive, you would weigh billions of times more than you do on Earth. Inside this object, ordinary atomic structure no longer exists. Under the immense pressure, electrons are forced into protons, combining to form neutrons. What was once an ordered arrangement of atoms has become a tightly packed sea of nuclear particles. The density is almost beyond imagination. A teaspoon of neutron star material would weigh as much as a large mountain. This compression turns the core into a single, continuous mass of neutrons held together by gravity and nuclear forces. The structure of a neutron star can be imagined in layers. At the surface, a thin crust of iron atoms remains, frozen solid by gravity and intense magnetic fields. Beneath that crust lies a region where nuclei are squeezed together so tightly that neutrons begin to leak out and move freely. Deeper still, the matter becomes a dense fluid of neutrons, mixed with small numbers of protons and electrons. In the core, conditions are so extreme that the exact composition is uncertain. Physicists debate whether it consists entirely of neutrons or whether more exotic particles, such as quarks, form there. These questions remain among the deepest mysteries of modern astrophysics. The forces inside a neutron star balance precisely. Gravity tries to crush the material further, while nuclear pressure resists that compression. If the mass is slightly greater, around 3 times the mass of the Sun, gravity wins, and the object becomes a black hole. But when the forces balance perfectly, the neutron star can remain stable for billions of years. It cools slowly, radiating the leftover heat from its violent birth, while continuing to spin rapidly in space. This rapid rotation is a consequence of angular momentum conservation. The original star, perhaps millions of kilometers wide, has now collapsed to a fraction of that size. Because no angular momentum is lost, its spin speed increases dramatically, like an ice skater pulling in their arms to spin faster. Some neutron stars rotate only a few times per second. Others spin hundreds of times each second. Their surface speeds can approach a significant fraction of the speed of light. At the same time, the magnetic field of the original star is compressed and intensified. Magnetic field lines that once extended across a large star are now concentrated into a much smaller area, increasing their strength to trillions of times that of Earth. These fields control the flow of charged particles near the surface and are crucial to producing the radiation that makes neutron stars visible as pulsars. From the outside, a neutron star may seem inert, a dark, cold remnant, yet it remains a highly dynamic system governed by extreme physics. Its internal structure holds clues about matter under conditions that cannot be recreated in any laboratory. For this reason, neutron stars are natural laboratories for studying the laws of nature at their limits. Many neutron stars remain hidden, detectable only through X-rays or gravitational influence. But when a magnetic pole aligns just right and beams radiation toward Earth, that neutron star becomes a pulsar, a rotating lighthouse of the universe. In the next part of the story, we will explore how rotation and magnetism combine to produce those rhythmic flashes that have become one of astronomy's most valuable signals. Every pulsar owes its distinct behavior to 2 connected properties: rapid rotation and intense magnetism. Together, these characteristics transform a silent neutron star into a cosmic beacon whose signals reach across thousands of light years. Understanding how they interact reveals why pulsars are so regular and why their pulses can be used as natural clocks. When a massive star collapses into a neutron star, its rotation rate increases dramatically. The conservation of angular momentum ensures that as the star's radius shrinks to a fraction of its original size, its spin must accelerate. A star that once rotated once every few days can now complete hundreds of rotations each second. This increase is not random. It is a direct consequence of physics. The smaller the radius, the faster the spin must become to conserve the same angular momentum. At the same time, the magnetic field of the original star is also conserved and compressed. Magnetic field lines that once extended across millions of kilometers are forced into a compact object only a few tens of kilometers wide. This concentration strengthens the field enormously, up to 1 trillion times stronger than Earth's. These magnetic forces influence charged particles around the neutron star, accelerating them to near light speed and producing powerful electromagnetic radiation. A pulsar's magnetic axis is usually tilted relative to its rotational axis. This misalignment is the key to its pulsing behavior. As the star spins, radiation is emitted from regions near the magnetic poles, forming narrow beams that sweep through space like the light from a rotating beacon. Each time one of these beams crosses Earth, radio telescopes detect a pulse of energy. The interval between pulses corresponds exactly to the star's rotation period. Because the rotation is so stable, these pulses arrive with astonishing regularity. Some pulsars are so consistent that their timing can be predicted months or even years in advance. They are more stable than the most advanced atomic clocks. Any small deviation from their predicted rhythm often signals an external cause, such as a companion star, a passing planet, or a slight slowing due to energy loss. Astronomers analyze these variations to study the environment around the pulsar and the physics of its motion. The radiation emitted by pulsars spans a wide range of wavelengths. Most were first discovered using radio telescopes, but many also emit X-rays and gamma rays. The radio pulses are easiest to detect because they penetrate interstellar gas with minimal interference. Each pulse lasts only a fraction of a second, but the repetition creates a clear and measurable pattern. The structure within each pulse can also reveal details about the pulsar's surface and magnetic configuration. Over time, the rotation gradually slows as energy is radiated away. This process, known as spin-down, is extremely slow. Some pulsars lose only a tiny fraction of a second over thousands of years. By measuring the rate of spin-down, astronomers can estimate a pulsar's age and magnetic strength. Younger pulsars spin faster and lose energy more quickly, while older ones rotate more slowly but with enduring consistency. The balance between speed, magnetism, and energy loss defines the long-term evolution of each pulsar. The combination of rotation and magnetism makes neutron stars some of the most efficient electromagnetic generators in existence. In laboratory terms, they act like enormous dynamos, converting rotational energy into radiation. The energy they release travels through interstellar space as perfectly timed signals. Each pulse is not just a flash of light but a record of the star's rotation, a precise, measurable mark of time. By the time those signals reach Earth, they have traveled for thousands of years, yet they still carry the pattern of the original spin. The universe itself becomes a transmitter, broadcasting the rhythm of its own mechanics. In the next segment, we will follow that first pulse as it leaves the newborn neutron star and begins its long journey through the darkness, a heartbeat of the cosmos that never truly fades. After a supernova fades and the debris expands outward, the newly formed neutron star begins to settle into its stable rhythm. Its rotation is fast, its magnetic field immense, and the surrounding space starts to fill with charged particles. These particles follow magnetic field lines that rise from the star's poles and arc far into space. As they accelerate, they emit radiation, radio waves, X-rays, and gamma rays that stream outward in tight beams. Each time the star rotates, those beams sweep through the surrounding void. For a distant observer, this motion appears as a repeating signal. When the beam points toward Earth, a short burst of energy is detected. When it moves away, the signal disappears. The result is a steady pattern of pulses that repeat with near-perfect regularity. The interval between them defines the pulsar's rotation period, sometimes one pulse every second, sometimes hundreds per second. What began as the chaotic collapse of a dying star has become a mechanism of precision. The first pulse of a newborn pulsar marks the transition from destruction to order. In that moment, gravity, magnetism, and motion reach balance. The star's rotation stabilizes, and its signal begins a journey that can last for millions of years. Each pulse travels through interstellar space, crossing regions filled with gas, dust, and magnetic fields. These obstacles scatter and delay the signal slightly, but not enough to erase its pattern. By the time the waves reach Earth, they carry both the signature of the pulsar and a record of everything they passed through along the way. Detecting those pulses requires sensitive radio telescopes. They convert faint radio waves into electronic data, producing plots of intensity versus time. When a pulsar's beam crosses our line of sight, the instrument records a brief spike, proof that the rotation has continued without pause. Astronomers then measure the exact interval between pulses and compare it with earlier observations. Over years, they find that many pulsars remain consistent to within microseconds. That accuracy allows scientists to treat them as natural clocks distributed throughout the galaxy. This precision is more than a scientific curiosity. It provides a stable reference frame for measuring motion, distance, and even the structure of space-time. By monitoring a group of pulsars together, astronomers can detect gravitational waves, tiny distortions that stretch and squeeze space itself. These discoveries link the physics of neutron stars to the deepest laws governing the universe. From a broader perspective, the first pulse is a reminder of how order can emerge from violence. A star collapses, yet from that collapse comes a rhythm so stable that we can measure it decades or centuries later. The same physical laws that created chaos also generate consistency. In that sense, pulsars illustrate the balance built into nature. Energy transforms, but patterns remain. For the listener, there is comfort in that regularity. The universe contains forces beyond comprehension, yet it also maintains predictable cycles. The steady rhythm of a pulsar mirrors the rhythm of breathing or a resting heartbeat. If sleep has not arrived yet, imagine that distant star turning steadily in the dark. Its signal repeats without effort, a quiet pattern, older and more reliable than any human-made clock. Let that rhythm set the pace for your own thoughts. The star will keep turning, time will keep flowing, and you can rest within that certainty. In the late 1960s, radio astronomy was still a young field. Scientists had learned that the universe was filled not only with light, but also with invisible radio waves emitted by stars, galaxies, and clouds of gas. These signals revealed processes that optical telescopes could never see. Among the people exploring this new frontier was a graduate student at the University of Cambridge named Jocelyn Bell. She worked under the supervision of astronomer Anthony Hewish, helping to build and operate a large radio array designed to study the flickering behavior of distant quasars. The telescope covered several acres of land and was connected to recorders that printed long streams of data on paper. Bell's task was to analyze the patterns, meter after meter of jagged lines, searching for changes in intensity. Most variations came from interference or the movement of celestial objects. But one day, she noticed something unusual. A series of small, perfectly spaced marks appearing at regular intervals. The pattern repeated every 1.3 seconds with absolute precision. It did not match any known astronomical source, nor did it resemble man-made interference from radar or satellites. The signal appeared night after night, always from the same direction in the sky. Its stability was remarkable. At first, Bell and her colleagues jokingly referred to it as LGM1, short for Little Green Men, because the regular timing suggested an artificial origin, but further observation soon ruled that out. A second, and later a third, similar source was found in different parts of the sky. The pattern could not possibly come from intelligent life at multiple distant points. Nature herself was producing these precise rhythms. After months of verification, the team realized they had discovered a completely new kind of celestial object. The regular pulses came from rapidly spinning neutron stars, remnants of supernova explosions whose magnetic fields and rotation created beams of radio energy. These objects were named pulsars, short for pulsating radio sources. The discovery provided the first direct evidence that neutron stars, which had previously existed only as theoretical predictions, were real. The scientific impact was immediate. Pulsars combined extreme density, strong magnetic fields, and rapid rotation in a way that allowed astronomers to study physical laws under conditions impossible to reproduce on Earth. Their regularity opened a new window into timekeeping and measurement at cosmic scales. The discovery also marked a milestone in the growing role of radio astronomy as a key branch of modern astrophysics. For Jocelyn Bell, the finding was both rewarding and challenging. As a young researcher, she had contributed one of the most important discoveries of the century, yet recognition initially went to her supervisor, who later shared the Nobel Prize. Over time, however, her contribution became widely acknowledged. Today, she is celebrated as one of the leading figures in observational astronomy. The precision she identified by hand, in endless meters of paper charts, revealed the heartbeat of the cosmos. From that first signal, scientists learned that the universe itself could produce order as exact as any human instrument. What appeared at first as a mystery became a foundation for decades of research. Pulsars were no longer curiosities. They became tools for exploring gravity, motion, and the passage of time across light years. That faint, repeating mark on a roll of paper in a Cambridge laboratory was the first recorded sign of a pulsar's steady rhythm. It showed that the universe does not simply expand in chaos, it also organizes itself in patterns so reliable that they can guide our understanding of space and time. In the next segment, we will look at how that realization changed astronomy forever, transforming the strange signal from a curiosity into one of the most important discoveries in modern science. After the first detection of the strange, regular signal, astronomers around the world began to pay attention. The Cambridge team confirmed that the pulses were not due to interference, instruments, or human error. The pattern was too stable and consistent. Soon, similar signals appeared in different parts of the sky, each with its own unique timing. The idea that these were artificial transmissions, perhaps from another civilization, quickly lost ground. Nature was the source, but understanding how it could produce such precision became the next great question. Researchers examined what kind of object could emit such rapid, repeating flashes. Ordinary stars could not rotate that quickly without tearing themselves apart, and planets lacked the energy to generate such intense radiation. The answer lay in theory. Physicists had long predicted that after a massive star exploded, its core could collapse into an incredibly dense remnant called a neutron star. These objects, only a few kilometers wide, could indeed spin several times per second without breaking apart. The combination of a small size, strong magnetic field, and rapid rotation provided an elegant explanation. As the neutron star rotated, its magnetic field lines guided charged particles outward, producing narrow beams of radio waves from the poles. If one of those beams happened to sweep past Earth, observers would detect a regular pulse of energy, exactly what Jocelyn Bell had recorded. The mystery signal was not a message, but a natural byproduct of physics operating under extreme conditions. Once this interpretation was proposed, it fit the observations perfectly. The period of each pulsar matched what theory predicted for neutron stars of various ages and strengths. Their slow, predictable spin-down over time corresponded to the gradual loss of energy through radiation. The phenomenon was consistent, measurable, and repeatable, three essential hallmarks of scientific understanding. Within a year, the term pulsar, short for pulsating radio source, entered the scientific vocabulary. The discovery had profound implications. Until that moment, neutron stars existed only on paper, as mathematical solutions to the equations describing stellar collapse. Now, they were confirmed as real astronomical objects. Pulsars demonstrated that the end of a star's life could produce not just destruction, but a stable structure that continued to interact with the universe. It was the first direct evidence that matter could exist in a state so dense that it defied normal atomic behavior. The recognition spread quickly. Radio observatories in Australia, the United States, and the Soviet Union soon detected dozens of pulsars across the sky. Each had its own unique timing signature, and their distribution revealed that these remnants were scattered throughout the Milky Way. Their regular signals provided astronomers with a new way to map the galaxy, probe interstellar gas, and study how radio waves travel through space. What had started as an unexplained pattern became a key instrument for understanding the structure of our universe. As the community embraced the new discovery, attention also turned to the people behind it. While Anthony Hewish received the Nobel Prize for the work, the foundational contribution of Jocelyn Bell, who first noticed the pattern, documented it carefully, and defended its significance, gained recognition over time. Her perseverance and scientific discipline remain an example of how observation, patience, and curiosity can lead to major breakthroughs. By the end of the decade, pulsars were no longer an oddity. They were a new class of celestial objects, each functioning as a natural metronome of the cosmos. The clarity of their signals gave scientists a tool unlike any other, a way to measure both time and space through the behavior of matter compressed beyond imagination. In the next segment, we will look more closely at what makes those pulses so consistent and how their patterns continue to refine our understanding of the universe. Once the true nature of pulsars became clear, astronomers began to study their signals in detail. Each pulsar emitted radio waves in bursts that repeated at perfectly regular intervals. By measuring these intervals precisely, researchers could determine the pulsar's rotation rate, its stability, and even its gradual slowing over time. What began as a curious flicker on a paper chart became one of the most reliable tools in modern astrophysics. The principle behind this precision lies in the rotation of the neutron star itself. Each pulse corresponds to one complete rotation, as the beam of radiation sweeps past Earth like the light from a turning beacon. The intervals between pulses can range from several seconds to less than 1,000th of a second, depending on how fast the pulsar spins. The most rapid pulsars, known as millisecond pulsars, rotate hundreds of times per second, maintaining near-perfect regularity. The timing accuracy rivals that of man-made atomic clocks. Astronomers soon realized that even the smallest variations in pulse timing carried valuable information. A slight change in the arrival time of pulses could indicate that the pulsar was moving relative to Earth, orbiting a companion star, or being influenced by interstellar material. These time delays, when analyzed across many pulsars, allowed scientists to measure distances, detect gravitational effects, and study the distribution of matter in the galaxy. Pulsars effectively became precise instruments for exploring space itself. To study them, observatories recorded long sequences of pulses and compared them to predictions. If the pulses arrived earlier or later than expected, the difference could be analyzed mathematically to reveal the cause. This method, known as pulsar timing, transformed radio astronomy into a science of measurement and precision. Over time, patterns emerged that confirmed the slowing of each pulsar's rotation, a process called spin down. As the star radiates energy, it gradually loses rotational speed, though the change is so small it can take centuries to notice. Some pulsars also exhibited sudden, brief changes in their rotation rate. These events, called glitches, occur when stresses in the star's crust are released, slightly altering its spin. Glitches reveal that neutron stars are not perfectly rigid, but contain layers capable of shifting and adjusting over time. Each observation adds detail to our understanding of how matter behaves at nuclear densities. The remarkable consistency of pulsars also made them excellent tools for testing physical theories. By comparing their timing against atomic standards, astronomers could measure how gravity affects the flow of time and verify predictions from Einstein's theory of relativity. Because the signals are natural and continuous, pulsars provide a stable, independent reference for studying fundamental laws of physics. Over the decades, thousands of pulsars have been catalogued, each with its own unique timing signature. When plotted together, these datasets create a map of the galaxy that reflects both structure and motion. Pulsars act as natural markers scattered through space, forming a kind of cosmic coordinate system. Their signals reach Earth from every direction, allowing scientists to measure the galaxy's size, density, and even its subtle motion through the universe. Perhaps most impressive is how long these stars remain predictable. Many pulsars have maintained stable timing for millions of years, continuing to emit pulses like cosmic timepieces that never stop. Even as they slowly lose energy, the relationship between rotation, magnetic field, and radiation remains consistent. Their reliability gives astronomy something rare, a phenomenon that behaves like a machine, yet is entirely natural. The discovery and study of pulsar timing marked a new era in astrophysics. It showed that precision could emerge from the violent remnants of stellar death, and that natural processes could rival human technology in stability. In the next segment, we will see how this realization gave rise to a new branch of astronomy, one that uses pulsars as tools to explore everything from gravity to the structure of spacetime itself. The discovery of pulsars in the late 1960s transformed radio astronomy from a developing science into one of the most precise tools for studying the universe. Before that time, radio telescopes were mainly used to detect broad emissions from galaxies, quasars, and interstellar gas. The signals were often diffuse, varying in strength and frequency. Pulsars changed everything by introducing a new kind of source, compact, predictable, and measurable with extraordinary precision. Once astronomers confirmed that pulsars were rotating neutron stars, observatories around the world began to reconfigure their equipment to detect them. Timing instruments were improved, recording systems refined, and analysis software developed to handle the rapid repeating signals. A new branch of astrophysics began to take shape, pulsar astronomy. Its focus was on understanding how these remnants behaved, how they evolved, and what they revealed about the laws of nature under extreme conditions. Each newly discovered pulsar added to the understanding of stellar evolution. Their positions in the sky showed that they were concentrated along the plane of the Milky Way, confirming their origin in massive stars that once lived and died within our galaxy. Their variety, some slow, others incredibly fast, indicated that pulsars change over time, spinning down as they radiate energy. Observing pulsars at different stages of their lifetimes allowed scientists to piece together a sequence of evolution from birth to eventual silence. The precision of their timing also encouraged international collaboration. Networks of observatories began to share data, comparing results across continents. Consistent monitoring from multiple locations reduced uncertainty and allowed astronomers to detect subtle variations that no single telescope could measure alone. This cooperative effort continues today through global timing arrays, which track dozens of pulsars simultaneously to look for gravitational waves and other large-scale cosmic phenomena. One of the most striking early discoveries was the existence of pulsars in binary systems. When a pulsar orbits another star, the timing of its pulses shifts slightly as it moves toward or away from Earth. These changes can be measured with exquisite detail, allowing scientists to determine the mass and orbital parameters of the system. Such measurements became critical tests for Einstein's general theory of relativity, confirming predictions about how gravity bends both light and time. Pulsars thus bridged observation and theory, linking practical measurement to fundamental physics. The growing catalogue of pulsars also helped map the galaxy's structure. The radio waves from each pulsar travel through clouds of charged gas between the stars. This gas slows the signals slightly, an effect called dispersion. By measuring dispersion, astronomers can estimate the amount of material between Earth and the pulsar, effectively turning each one into a probe of interstellar space. Over time, these measurements built a three-dimensional picture of the Milky Way's composition and density. Pulsar astronomy quickly became a cornerstone of modern astrophysics. It connected the smallest and largest scales of the universe, subatomic forces within neutron stars, and the structure of galaxies stretching across hundreds of thousands of light-years. It also demonstrated how precision and patience could reveal new truths hidden in the faintest signals. Perhaps most importantly, pulsars gave scientists a new way to think about time. They showed that the universe contains its own natural metronomes, operating without interference or decay for millions of years. By listening to them, humanity gained not just data but perspective, a reminder that order exists even in the aftermath of chaos. In the next segment, we will see how astronomers began to chart the galaxy through these rhythmic signals, turning their collection of data into a map of the Milky Way built not from light, but from time itself. After pulsars were recognized as rotating neutron stars, astronomers realized that these cosmic clocks could do more than test theories. They could help map the structure of the galaxy itself. Each pulsar sits at a known point in the Milky Way, sending out radio signals that travel vast distances to reach Earth. Along the way, those signals pass through clouds of gas and charged particles. By studying how the pulses change as they move through space, scientists can learn about both the pulsars and the material between them. When radio waves travel through interstellar plasma, they slow down slightly depending on their frequency. Higher frequency waves arrive sooner, and lower frequency waves arrive later. This effect, called dispersion, acts like a fingerprint of the space between us and the pulsar. By measuring how much the lower frequencies lag behind the higher ones, astronomers can calculate the amount of free electrons in the signal's path. The greater the delay, the denser or longer the route through the galaxy. Each pulsar therefore provides two valuable pieces of information: its exact position in the sky and an estimate of how much material lies between it and Earth. When these data are combined across hundreds of pulsars, they form a map of the Milky Way's hidden structure. The galaxy's spiral arms, filled with dust and ionized gas, can be traced not just by light but by timing, the steady beat of pulsars marking distance and density like milestones in space. This mapping work has refined our understanding of galactic dimensions. Before pulsar astronomy, the Milky Way's scale and shape were estimated mainly from optical observations. Those views were often blocked by dust. Pulsar timing provided a way to see through that obscuring material. Radio waves penetrate the dust, and their dispersions reveal how much matter lies along each line of sight. Over time, the results confirm that our galaxy spans roughly 100,000 light-years and contains complex networks of gas clouds, magnetic fields, and energetic particles. Pulsars also help measure motion. As the Earth orbits the Sun and the Sun moves through the galaxy, the timing of pulsar signals shifts slightly. By tracking these changes across many sources, astronomers can refine our models of solar and galactic motion. Some even use pulsars as fixed reference points in the sky, functioning like celestial coordinates that remain stable for decades or longer. They provide an external frame of reference, one that is not tied to any planet or spacecraft, but to the galaxy itself. Beyond mapping, pulsars offer a way to study how the interstellar medium evolves. Changes in pulse dispersion over time indicate fluctuations in gas density along the line of sight. By comparing data collected over years, scientists can detect shifts caused by stellar winds, magnetic turbulence, or moving clouds of plasma. The precision of these observations turns what were once invisible processes into measurable phenomena. The combined data from pulsars across the sky form what is sometimes described as a timing grid. Each pulsar contributes a line of information that, when added together, reveals patterns on galactic scales. Astronomers now use this grid to test fundamental ideas about how energy and matter interact in space. It serves as a foundation for projects such as pulsar timing arrays, which rely on this same principle to search for gravitational waves, distortions in space-time caused by massive objects like black holes. By transforming isolated signals into a global network, pulsar astronomy turned timekeeping into cartography. Each pulse recorded on Earth represents not just the rotation of a star, but a data point in the galaxy's structure. What began as a single repeating signal has become a coordinated system linking hundreds of stars across tens of thousands of light-years. In the next segment, we will pause from the scientific expansion to reflect on the role pulsars play as stable rhythms in an ever-changing universe, how their precision and consistency remind us that even in deep space, order persists amid motion. After the years of discovery and measurement, the story of pulsars carries with it more than scientific value. Their steady rhythm offers something deeper, a reminder that the universe, even at its most extreme, maintains order and predictability. Each pulse we detect represents not just the rotation of a collapsed star, but the persistence of physical laws that never falter. There is something quietly reassuring about that. When radio telescopes listen to a pulsar, the signal appears as a simple pattern, a rise and fall of energy, steady as a clock. The intervals remain constant across time and distance. These rhythms are precise enough to measure motion on galactic scales, yet simple enough to be recorded as a series of regular beats. In a way, they reflect the same principles that guide life on Earth. Just as the day follows the night and the seasons repeat, the pulses of neutron stars continue without interruption, marking time in the vastness of space. For astronomers, this predictability provides a reference against which everything else can be measured. For the rest of us, it can serve as a metaphor for stability. The same universe that produces storms and collisions also sustains patterns that endure for millions of years. Pulsars are a symbol of continuity, a reminder that even the forces that destroy can also create order. If you are listening at night, you may find comfort in the idea that somewhere far beyond the solar system, these natural clocks are still turning, their light does not waver, and their rhythm does not break. They will continue to emit their signals long after our own generation has passed, and long after Earth itself has changed. The regularity of their pulses mirrors the steady rhythm of breathing, the quiet repetition that signals rest and recovery. You can think of the universe as holding its own form of calm, a background order that persists beneath the surface of motion and noise. Pulsars are evidence of that calm. They show that even in the aftermath of violent explosions, the laws of nature find equilibrium. The star collapses, energy stabilizes, and time finds a new way to continue. As you listen now, you may notice that your own body also follows predictable cycles. The heart beats, the lungs expand and contract, and the mind slows its activity when given a steady rhythm to follow. This connection between pattern and peace is not coincidence. It is part of how living systems maintain balance. The human body and the distant star both rely on repetition to sustain order. If sleep has not yet arrived, there is no need to seek it actively. Let the idea of those distant pulses be enough. Imagine them continuing quietly in the background of the universe, unaffected by distance or time. Each one is a rotation, a mark of stability in a restless cosmos. With that thought, allow your breathing to settle into its own rhythm. The same physical principles that keep the pulsar spinning also keep your world in motion, steady, balanced, and unbroken. The sky above may seem silent, but across it countless neutron stars continue to turn, each one keeping time with the universe. As their pulses travel across light years to reach us, they form a pattern that connects everything bound by physics and energy. That pattern can serve as a reminder of permanence and peace. The stars keep their rhythm so that you can rest within yours. Pulsars are remarkable not only for their precision but also for their gradual change. Over time, their rotation slows, revealing how energy leaves the system. This process, known as spin down, is one of the key ways scientists learn about a pulsar's age and strength. Even though these stars appear timeless, their timing tells a quiet story of transformation. The slowing occurs because a pulsar constantly emits energy. Each pulse represents the loss of a tiny fraction of the star's rotational energy. The radiation it releases, radio waves, X-rays, and gamma rays, requires power, and that power comes from the pulsar's spin. As the neutron star continues to radiate, it gradually converts its immense rotational energy into electromagnetic waves and particle winds. The effect is small but measurable. Over years or centuries, the interval between pulses increases slightly, showing that the star is turning a little more slowly than before. Astronomers measure this change with extraordinary precision. By comparing pulse timings across long periods, they can calculate how fast a pulsar's rotation is decreasing. The rate of slowdown, combined with the current spin period, provides an estimate of the pulsar's characteristic age, an approximation of how long it has been emitting. Younger pulsars spin rapidly, often several times per second, while older ones rotate more slowly. This relationship helps researchers build a timeline of stellar evolution after a supernova. The energy loss also reveals the pulsar's magnetic field strength. A stronger magnetic field creates greater braking, leading to a faster spin down. The most powerful pulsars, called magnetars, slow quickly as their magnetic forces dominate the emission process. Others, with weaker fields, can maintain their rhythm for millions of years. Each pulsar's unique rate of deceleration reflects a balance between its rotational energy and magnetic intensity. While the change in speed is imperceptible in human terms, it represents an enormous flow of energy. A typical pulsar releases more power than the sun, even though it is only a few kilometers wide. Most of this energy is carried away by relativistic particles and magnetic radiation, forming nebulae that can remain visible long after the supernova fades. The famous Crab Nebula, for example, still glows brightly because of the energy supplied by its central pulsar. Observing such systems allows astronomers to connect visible remnants with the physics of their hidden cores. Sometimes, a pulsar's slowdown is interrupted by sudden, brief increases in rotation rate known as glitches. These events are thought to result from small rearrangements inside the neutron star, where the solid crust interacts with a superfluid interior. When stresses build up and are released, the star spins slightly faster for a short time. Glitches offer rare glimpses into the internal structure of neutron stars, confirming that they are not solid throughout but composed of layers with different properties. Eventually, a pulsar's rotation becomes too slow to generate strong electromagnetic emission. When that happens, its beams fade, and it effectively becomes invisible to radio telescopes. The star itself remains, but its clock no longer ticks in a way we can detect. This quiet phase marks the end of a pulsar's active life. Yet even in silence, it remains a record of past energy, a compact relic of a once brilliant star. Spin down demonstrates a principle that extends beyond astronomy. Every system loses energy over time, Yet within that loss lies a record of its history. By measuring how pulsars slow, scientists can reconstruct their past, understand their environment, and predict their future. Each change in timing, measured across years, is a note in a vast symphony of gradual transformation. The universe keeps precise accounts, and pulsars serve as its most dependable witnesses. Not all neutron stars behave in the same way. Within the family of pulsars exist two remarkable extremes that show how flexible and varied these stellar remnants can be. Magnetars, with their immense magnetic fields and sudden bursts of energy, and millisecond pulsars, the fastest rotating objects known in the universe. Together they demonstrate the range of physical possibilities that occur when matter is compressed to the limits of nature. A magnetar is a neutron star with a magnetic field so intense that it distorts the space around it. Typical pulsars have magnetic fields a trillion times stronger than Earth's, but magnetars exceed even that by a factor of up to 1,000. Their fields can twist the crust of the star, generating sudden releases of energy in the form of X-rays and gamma rays. These outbursts can temporarily outshine all other sources in their region of space. Magnetars are rare and short-lived because their extreme magnetism drains their rotational energy rapidly. They spin down within a few thousand years, leaving behind faint remnants once their magnetic fields decay. The physics behind these events pushes the boundaries of what is possible. The magnetic pressure near the surface of a magnetar is so strong that it can rearrange atomic nuclei and change the behavior of matter itself. During a flare, the crust can crack under the strain, releasing vast amounts of energy in a fraction of a second. Detectors on Earth record these events as powerful bursts of radiation arriving from distant points in the sky. Each one provides insight into the relationship between magnetism, gravity, and quantum processes at nuclear densities. On the opposite end of the spectrum are the millisecond pulsars, neutron stars that rotate hundreds of times per second. Their speed is not simply a leftover from birth, it is often renewed. Over time, some neutron stars draw in matter from a nearby companion star. As the gas spirals inward, it transfers angular momentum, causing the neutron star to spin faster. This process, called recycling, effectively gives the pulsar a second life. The result is a stable, rapidly rotating object, whose pulses arrive with extraordinary precision. Millisecond pulsars are among the most stable natural clocks in existence. Their timing variations can be smaller than 1 microsecond over many years. Because of this stability, they play a central role in modern astrophysics. Scientists use them as part of pulsar timing arrays, networks that monitor many pulsars at once to detect gravitational waves and measure cosmic distances. The constancy of these fast rotators allows astronomers to treat them as fixed points of reference scattered throughout the galaxy. Despite their differences, magnetars and millisecond pulsars are connected by a common origin. Both began as massive stars that collapsed under gravity. Their contrasting behaviors depend on factors such as mass, magnetic field strength, and environment. Magnetars represent youth and instability, dominated by magnetic power. Millisecond pulsars represent age and balance, sustained by the steady input of angular momentum from their surroundings. Together, they define the limits of what a neutron star can become. Studying these extremes has expanded our understanding of how energy is stored and released in the universe. Magnetars show how magnetic fields can reshape matter. Millisecond pulsars show how stability can emerge from interaction and renewal. Both challenge and refine the equations of physics. Observing them reminds us that the cosmos contains not just patterns but diversity, an entire range of behaviors arising from the same fundamental forces. In the next segment, we will explore another frontier of pulsar science. What happens when two neutron stars orbit each other? These systems have provided some of the strongest evidence yet for one of Einstein's most profound predictions, the existence of gravitational waves. Among the many kinds of pulsars discovered, those found in binary systems, paired with another star or neutron star, proved especially valuable for testing the laws of physics. In such systems, the pulsar's precise timing acts like a cosmic stopwatch, recording the effects of gravity on motion and time. These observations have provided some of the most convincing evidence that gravitational waves, ripples in the structure of space-time, are real. When two massive objects orbit one another, they interact through gravity, curving space-time around them. According to Einstein's general theory of relativity, this motion should generate gravitational radiation, energy carried away as waves that travel at the speed of light. For decades, these waves were predicted but not yet directly detected. Pulsar binaries offered a natural laboratory for observing their indirect effects. In the 1970s, astronomers Russell Hulse and Joseph Taylor discovered a pulsar orbiting another neutron star. Careful monitoring of its pulse timing revealed that the orbit was gradually shrinking. Each year, the two stars moved slightly closer together, and the rate of change matched the amount of energy that would be lost through gravitational radiation, as predicted by Einstein's equations. The discovery confirmed that gravitational waves were not just a theoretical possibility, they were a measurable reality. Hulse and Taylor later received the Nobel Prize for this work, which became one of the strongest confirmations of relativity ever recorded. The precision of pulsar timing made these measurements possible. Each pulse arrived with consistent spacing, allowing astronomers to track even the smallest variations in orbital motion. When the pulsar moved toward Earth, its pulses arrived a little sooner. When it moved away, they arrived slightly later. By plotting these changes over months and years, scientists could map the orbit with remarkable accuracy. The results showed that the system was losing energy exactly as predicted by the emission of gravitational waves. Binary pulsars continue to be essential tools for gravitational research. Some systems are even more extreme than the original discovery. Double pulsars, in which both stars emit detectable pulses, allow for independent tracking of each object. Observing such systems gives scientists multiple lines of data, enabling tests of relativity under stronger gravitational fields than those found anywhere else. Beyond confirming Einstein's theory, binary pulsars help measure other key properties of the universe. They provide information about the masses of neutron stars, the behavior of matter under immense pressure, and the dynamics of stellar evolution. In some cases, the precise timing data reveals small distortions caused by the gravitational influence of unseen companions, offering clues about planets or smaller bodies orbiting these dense stars. Pulsar binaries have also become part of broader efforts to detect gravitational waves directly. While instruments like LIGO and Virgo detect high-frequency waves from colliding black holes, pulsar timing arrays use networks of millisecond pulsars to search for slower, galaxy-scale waves produced by merging supermassive black holes. In this approach, the pulsars themselves act as a giant, intergalactic detector. When a gravitational wave passes through our region of space, it slightly shifts the timing of pulses arriving from multiple directions. By analyzing these coordinated shifts, astronomers can infer the passage of the wave across the Milky Way. The study of binary systems shows how nature provides both the source and the instrument for discovery. The same forces that bend space-time create the tools we use to measure it. A collapsed star, spinning with perfect rhythm, becomes a signal by which we confirm the structure of the universe. In the next segment, we will examine how this precision has evolved into a new generation of experiments that turn pulsars into sensors for detecting the faintest vibrations of space-time, the pulsar timing arrays that extend Einstein's theory into practice across the entire galaxy. After binary pulsars confirmed the existence of gravitational waves, scientists began to imagine how these faint distortions of space-time could be studied on even larger scales. Instead of relying on a single pair of stars, they looked to a network of pulsars scattered across the galaxy. Because pulsars emit signals with extraordinary precision, their combined timing could serve as a vast detector, an instrument made not of metal or glass, but of stars themselves. This concept became known as the pulsar timing array. A pulsar timing array functions like a cosmic grid. Astronomers monitor dozens of millisecond pulsars located in different parts of the Milky Way, measuring the arrival times of their radio pulses with extreme accuracy. If a gravitational wave passes through our region of space, it slightly stretches and compresses space-time as it moves. This change is incredibly small, altering the distance between Earth and a pulsar by less than the width of an atom. But because the pulsar's pulses are so consistent, even such minute shifts can be detected as slight deviations in their arrival times. When researchers compare timing data from many pulsars, they look for correlated variations, a subtle pattern appearing across the sky. If several pulsars show synchronized changes in their timing, the most likely explanation is that a gravitational wave passed through the space between them and Earth. In this way, pulsar timing arrays act as galaxy-sized observatories, sensitive to waves far longer and slower than those detected by ground-based instruments like LIGO or Virgo. These long-period gravitational waves are thought to come from some of the most massive objects in the universe, pairs of supermassive black holes orbiting each other at the centers of merging galaxies. As the black holes spiral together, they generate ripples that can take years to cross a single wavelength. Detecting these waves allows scientists to study cosmic events occurring over vast timescales, processes that shape galaxies and influence the large-scale structure of the universe. The practical challenge lies in precision. Measuring the arrival times of pulses from many different stars requires stability over decades. Each pulsar must be observed regularly, and the data corrected for every possible influence: the motion of Earth, the effect of interstellar gas, and even the tiny irregularities in the atomic clocks used to record time. Coordinating this work has become a global effort. Projects such as Nanograv in North America, the European Pulsar Timing Array, and the Parkes Pulsar Timing Array in Australia share data through the International Pulsar Timing Array collaboration. Together they form a worldwide experiment, monitoring the galaxy's most stable clocks in search of faint tremors in spacetime. Recent results suggest that these collective efforts are beginning to detect a background of gravitational waves, a constant hum produced by countless distant sources. Rather than a single signal, it is a pattern emerging from the combined influence of many supermassive black hole pairs. This discovery would mark the first time humanity has observed gravitational activity on galactic scales, extending Einstein's theory of relativity into an entirely new domain. The idea that natural objects, separated by thousands of light years, can work together to measure distortions in the universe is extraordinary. No human technology could span such distances, yet the cosmos provides the tools itself. Pulsars, created in stellar explosions, now serve as instruments for detecting the movement of space-time, proof that even in their decay, stars contribute to our understanding of order. In the next segment, we will look at how this precision has redefined what we mean by time itself, and how pulsar timing now rivals and, in some ways, surpasses the accuracy of the finest atomic clocks built on Earth. The more astronomers studied pulsars, the clearer it became that these objects are not just remnants of dying stars, they are among the most accurate timekeeping systems in existence. Their pulses arrive with such stability that they can be used as benchmarks to test the performance of atomic clocks on Earth. Some pulsars are so regular that they lose less than a billionth of a second over an entire year, a level of precision unmatched by most human-made instruments. Each pulse is a record of rotation. Because the physics that govern a neutron star's spin are consistent, its period remains constant for long stretches of time. When small variations do occur, they are predictable and measurable. This allows astronomers to build models that account for every known influence, from the star's gradual energy loss to the motion of Earth in its orbit. The result is a timing system that can be projected forward or backward with extreme reliability. Millisecond pulsars, in particular, stand out for their precision. These rapidly rotating neutron stars complete hundreds of revolutions each second. Their signals are sharp and repetitive, producing clean, measurable pulses that can be tracked over decades. When a network of these pulsars is observed together, they create a natural time standard for the galaxy, an interstellar version of coordinated universal time. Comparing pulsar timing with atomic clocks has helped refine both. On Earth, the world's most accurate atomic clocks use the vibrations of atoms, usually cesium or ytterbium, to define the second. But even these instruments are limited by environmental factors such as temperature and mechanical stability. Pulsars, by contrast, are not affected by local conditions. Their consistency arises from fundamental forces acting over cosmic distances. By aligning terrestrial time with pulsar signals, scientists can detect and correct small irregularities in atomic timekeeping systems, improving long-term precision. This interaction between natural and artificial clocks also strengthens navigation and measurement technologies. For example, spacecraft can use pulsar timing as a form of deep space navigation, comparing the arrival times of pulses from multiple known sources to determine position. Unlike satellite-based systems such as GPS, pulsar signals are available everywhere and are stable for millions of years. Future missions beyond the solar system may one day rely on these cosmic beacons as reference points. The implications go beyond practical applications. Pulsars have reshaped our understanding of time itself. They show that time can be measured not only by human instruments but also by natural processes occurring far beyond our world. The rotation of a neutron star becomes a unit of stability written into the structure of the universe. It suggests that precision is not an invention of technology but an intrinsic feature of nature, observable wherever matter and motion find equilibrium. The study of pulsar timing continues to refine our definition of time. Astronomers now combine pulsar data with atomic standards to create composite timescales that remain stable over decades. These systems provide a cross-check between human-made and cosmic precision, ensuring that the measurement of time remains consistent across both Earth and space. In effect, the universe itself contributes to our calibration. It is remarkable to think that what began as a collapsing star, a violent end to a stellar life, has become one of the most steady and predictable sources of rhythm in existence. Pulsars reveal that even at the edge of physics, order persists. Their regularity demonstrates that the same laws governing subatomic particles also shape phenomena on galactic scales. In the next segment, we will return to the quieter, reflective side of this story and explore how these immense and distant clocks connect to something familiar: the human experience of rhythm, rest, and the slow drift towards sleep. When scientists describe pulsars as precise clocks, they are referring to more than their timing. They are describing the calm that comes from predictability. Each pulse marks a rotation that has continued, unchanged, for millions of years. The intervals between signals are measured in fractions of a second, yet they repeat with near-perfect regularity. In that steadiness lies a kind of quiet reassurance, a reminder that even in the violent aftermath of a supernova, order takes shape and endures. Radio telescopes record these pulses as patterns of peaks and troughs. What the data represent is motion converted into rhythm, a star turning steadily in the dark. Some pulsars rotate hundreds of times per second, others only once or twice, but all share that same constancy. The universe, through them, maintains a rhythm of its own. Every pulse that reaches Earth has traveled for thousands of years, yet still arrives on schedule. The predictability is complete enough that astronomers can tell when the next one will appear to within microseconds. That reliability can be comforting to think about. Life on Earth often feels unpredictable, but the cosmos runs on principles that do not change. Matter behaves the same way everywhere. Gravity pulls, light travels, and neutron stars turn. When we observe them, we are reminded that some systems are free from uncertainty. The pulsar's rotation will not pause because of weather, time zones, or human distraction. It continues silently, performing its task with no intention other than to follow the rules of physics. If you are listening now, the same regularity that helps scientists measure time can help you slow your own. You might imagine the universe filled with countless invisible clocks, each one turning at its steady pace. Together, they form a pattern of quiet consistency that stretches through the galaxy. This thought does not require imagination in the poetic sense, it is scientific fact. Those rotations are happening now, their signals crossing space, their timing precise. Let the concept of that rhythm shape your own breathing. A pulsar turns, you breathe in. Another pulse, you breathe out. The scale is vastly different, but the process is the same, energy repeating itself in cycles. There is no need to match the rhythm consciously. Simply knowing it exists can bring a sense of alignment, a connection between your small, immediate world and the larger patterns of the universe. Pulsars show that even the universe has a form of rest. Between each pulse is a silence measured in fractions of a second, a pause before the next signal begins. Those moments of stillness are part of the rhythm. They define it as much as the pulses themselves. In the same way, sleep and wakefulness are not opposites but parts of one repeating process. Rest is not a stop, it is the space between beats. If sleep is close, you can allow these thoughts to fade into background noise, like the quiet hum of the cosmos itself. If it has not yet come, there is no need to reach for it. The pulsars continue to turn whether or not we notice them. Time flows evenly, carried by the steady rotation of collapsed stars and by the slower, gentler rhythm of your own body at rest. Both are bound by the same physical laws. Both are stable, continuous, and self-sustaining. Across the galaxy, neutron stars keep turning, their signals arriving on time, their rhythm unchanged. The precision they hold is the universe's way of showing balance. Within that balance, you can rest. Let the regularity of those distant rotations remind you that calm is not the absence of movement but the predictability within it. Long before pulsars were discovered, navigation relied on steady points of reference. Sailors guided their ships by the sun and stars. Pilots later used radio beacons and satellites. In deep space, however, no fixed landmarks exist. Once a spacecraft leaves Earth's orbit, it moves through a region where light takes minutes or hours to travel between points. Communication delays make real-time guidance impossible. For this reason, scientists have turned to pulsars, natural, dependable sources of timing, as a potential solution for interstellar navigation. Each pulsar emits regular pulses that can be predicted far in advance. Because the timing and position of many pulsars are well known, a spacecraft can use them the same way a GPS receiver uses satellites. By measuring the exact arrival time of pulses from several different pulsars and comparing them with predicted times, the craft can determine its own position in space. The difference between expected and observed arrival times reveals the spacecraft's distance relative to each pulsar. When data from multiple sources are combined, the intersection of those measurements pinpoints location and speed. This approach is known as X-ray pulsar navigation, often abbreviated as XNav. The idea was first tested in the early 21st century using the NICER telescope aboard the International Space Station. NICER, designed primarily for studying neutron stars, also demonstrated that pulsar signals could provide autonomous navigation without contact from Earth. During these tests, the system measured arrival times from several well-known millisecond pulsars and calculated the station's orbit to within a few kilometers. Although still less precise than Earth-based GPS, the principle worked exactly as predicted. Pulsar navigation has unique advantages. Unlike satellite systems that depend on ground control, pulsars are available everywhere and operate continuously. Their signals are unaffected by interference, weather, or power loss. A network of carefully selected pulsars could serve as a permanent galactic reference frame, allowing spacecraft to orient themselves anywhere within the Milky Way. Because millisecond pulsars maintain such extraordinary timing stability, they can provide location updates over years without recalibration. Implementing this system requires specialized detectors capable of observing X-ray or radio emissions. X-ray detection is often preferred because the signals are stronger and less distorted by interstellar gas. Compact X-ray telescopes can fit aboard spacecraft, enabling autonomous operation far from Earth. In principle, future probes traveling to the outer planets, or even beyond the solar system, could rely on pulsars for continuous guidance. Each pulse, measured and compared, would confirm position in 3 dimensions. This method transforms the galaxy into a natural navigation network. Each pulsar acts as a beacon, flashing with a rhythm known to anyone listening. The distances involved are enormous, but the physics remains simple. The difference between when a pulse is predicted to arrive and when it is actually detected reveals how far light has traveled in that interval. From this, computers can calculate position with no external input. Navigation becomes an act of measurement against the universe's most stable clocks. Beyond its practical applications, Pulsar navigation represents a philosophical milestone. For the first time, humanity has a navigation system that does not depend on Earth. The same signals used to test theories of relativity now serve as guides for exploration. It means that even in the emptiness between stars, there are reliable points of reference, steady markers that confirm where we are and how we move through the cosmos. In the next segment, we will explore how the same precision that enables navigation also allows scientists to measure distances, masses, and the scale of the galaxy with accuracy that once seemed unreachable. Pulsars are not only timekeepers and navigational beacons, they are also powerful measuring tools. The precision of their signals allows scientists to calculate distances across the galaxy and determine the masses of objects that cannot be observed directly. Each pulse carries more than information about rotation. It also records how space itself affects the signal on its journey to Earth. One of the primary ways astronomers measure distance to a pulsar is through dispersion. As radio waves travel through the interstellar medium, they slow slightly depending on their frequency. Lower frequency waves are delayed more than higher ones. By measuring this delay, known as the dispersion measure, scientists can estimate the amount of ionized gas between Earth and the pulsar. When combined with models of galactic gas distribution, this provides a reliable estimate of distance. Though indirect, the method works remarkably well and has been verified through parallax measurements using radio interferometry. In some cases, pulsars can be used to measure distances with even greater precision through timing parallax. As Earth moves around the Sun, the pulsar's apparent position shifts slightly, just as nearby objects appear to move against a distant background when you change viewpoint. These shifts, recorded in the timing of pulses, can be used to calculate the pulsar's actual distance from Earth. Such measurements allow astronomers to map the galaxy with accuracy down to light years, an achievement once thought impossible without optical data. Pulsars also enable scientists to measure mass, both of themselves and of other bodies in their systems. When a pulsar is part of a binary pair, the precise timing of its pulses reveals details of the orbit. Small changes in pulse arrival times, caused by the pulsar's motion toward and away from Earth, can be analyzed to determine orbital speed and shape. Using these data, astronomers apply Newtonian and relativistic physics to calculate the masses of both the pulsar and its companion. This method has produced some of the most accurate stellar mass measurements ever obtained. For instance, in systems where the companion is another neutron star or a white dwarf, timing observations allow for tests of gravitational theory. The motion of the pair, the bending of radio waves by gravity, and the shifting of pulse frequencies all contribute to a precise model of how gravity behaves under intense conditions. These systems have helped confirm that neutron stars typically have masses between about 1 and 2 times that of the Sun, compressed into a sphere barely 20 kilometers across. Beyond single systems, pulsar measurements help determine the mass distribution of the Milky Way itself. By analyzing how pulses are delayed by interstellar gas and gravitational fields, scientists can infer where matter is concentrated and how it moves. Each pulsar becomes a probe, sampling a different part of the galaxy, and together they reveal its large-scale structure. The information gathered from hundreds of pulsars forms the foundation for models of galactic density, spiral arm shape, and magnetic field strength. These measurements are not only theoretical, they have practical implications for astrophysics, cosmology, and navigation. Accurate distance and mass estimates allow for better predictions of gravitational interactions, orbital dynamics, and even the expansion rate of the universe. Pulsars act as natural calibration points for a variety of measurements, extending the reach of science far beyond the solar system. Every pulse received on Earth has crossed space shaped by gravity, matter, and time. By decoding its subtle variations, astronomers transform each signal into a measurement of the universe itself. The precision of these measurements continues to improve as technology advances, linking human instruments to the most stable clocks nature provides. In the next segment, we will look at how pulsars help scientists test the predictions of relativity in greater depth, particularly through the study of double pulsar systems, where gravity's influence can be observed with unmatched clarity. Few natural systems test the limits of physics as effectively as pulsars. These dense, rapidly rotating stars exist in environments of gravity and pressure far beyond anything that can be created in a laboratory. Their precise signals allow scientists to examine how time, motion, and gravity interact, key principles described by Einstein's general theory of relativity. Each pulse from a neutron star is both a clock tick and an experiment, demonstrating the workings of space-time on the edge of physical possibility. Relativity predicts that gravity affects time. In strong gravitational fields, time passes more slowly. This phenomenon, known as gravitational time dilation, can be measured directly in systems where a pulsar orbits another massive body. As the pulsar moves closer to its companion, its pulses arrive slightly later. As it moves away, they arrive sooner. The difference matches exactly what relativity predicts for the changing gravitational potential along its orbit. The same pulses that reveal motion also confirm that time itself stretches and contracts in measurable ways. The most detailed confirmations of relativity come from double pulsar systems, where both stars emit detectable radio pulses. These rare pairs allow astronomers to track each object's motion independently. Every pulse carries information about orbital speed, distance, and the curvature of space-time between the two stars. Over months and years, the observed variations align perfectly with Einstein's equations. In some cases, scientists have measured orbital decay due to gravitational wave emission with an accuracy of better than 1 part in 1,000, precision unmatched by any other natural phenomenon. Another relativistic effect observed in pulsar systems is Shapiro delay. When the pulsar's signal passes close to its companion star, the curvature of space-time causes the radio waves to take slightly longer to reach Earth. This delay, though only microseconds long, provides direct evidence of how mass warps space. Measuring it enables astronomers to calculate the companion's mass and confirm the relationship between gravity and light. The consistency of these measurements across different systems leaves little doubt that relativity holds true even in the universe's most extreme environments. Pulsars have also helped test whether the constants of nature truly remain constant. By comparing the timing of signals over decades, researchers can look for subtle changes in physical laws, shifts that might indicate new physics beyond Einstein's model. So far, no such variations have been found. The pulses remain aligned with predictions, suggesting that the universe's fundamental laws are indeed stable across time and space. The importance of these findings extends beyond astrophysics. Technologies such as GPS navigation and satellite communication rely on corrections derived from relativity. Without accounting for time dilation, their precision would drift by kilometers each day. Pulsar studies provide continual verification that those corrections remain accurate. The same principles that govern distant neutron stars ensure that our systems on Earth function correctly. The reliability of pulsars also allows scientists to probe questions about gravity's limits. For example, by observing systems where a pulsar orbits a white dwarf, researchers can test whether gravity behaves differently for objects of different composition, a key prediction of some alternative theories. So far, every test continues to support Einstein's original framework. Through these experiments, pulsars act as natural laboratories scattered across the galaxy. Each one is a self-contained test of physics, operating under immense gravity and energy. The results show that even at these extremes, the same equations describe reality with stunning precision. The next segment will turn to what these findings mean for our understanding of the universe itself. How pulsars help define not only the behavior of matter and time, but also the broader concept of cosmic order and stability. Every pulsar, in its precision, tells a story about order. The universe may appear chaotic from a distance, filled with collisions, explosions, and unpredictable motion, but at its core, it follows patterns that remain consistent over billions of years. The rhythmic signals of pulsars are one of the clearest examples of that hidden order. They show that even in the aftermath of destruction, the laws of nature reassert themselves with calm, mathematical discipline. When a massive star collapses, it does not end in randomness. Instead, its mass, rotation, and magnetic field settle into balance. The result is a neutron star, governed by the same physical equations that describe everything from electrons to galaxies. The precision of pulsars emerges naturally from these laws. No external system forces them to remain regular, they simply obey the principles built into the universe. This intrinsic order is what allows scientists to trust the results of their observations. Every pulse confirms that the same rules apply everywhere, from the smallest atom to the largest spiral galaxy. The predictability of pulsars helps reveal how structured the cosmos truly is. Their signals show that time and energy interact consistently across unimaginable distances. A rotation measured near a supernova remnant behaves identically to one observed thousands of light-years away. The same constants govern both events. This uniformity forms the foundation of science itself, the assumption that nature's laws are universal. Pulsars provide proof of that principle, visible not through theory alone but through direct observation. Even the slow decay of a pulsar's spin follows a precise pattern. The energy it loses through radiation diminishes predictably, allowing astronomers to project its future and reconstruct its past. Such stability in behavior suggests that the universe does not drift aimlessly, it evolves in measurable, comprehensible ways. What might seem like chance at one scale becomes symmetry at another. For those who study them, pulsars inspire more than data collection. They embody a kind of cosmic rhythm that links mathematics to existence. Their pulses remind scientists that the universe is both dynamic and ordered, capable of sustaining motion without chaos. Each rotation is a statement of continuity, matter transformed into motion, motion into light, and light into information that can cross the galaxy unchanged. The presence of this order also carries philosophical weight. It suggests that structure and stability are not human inventions but natural outcomes of physical reality. Wherever gravity, magnetism, and energy interact, they organize themselves into patterns. From atoms to stars, the same tendency toward equilibrium appears again and again. Pulsars are visible proof of that universal tendency, repetition born not from design but from the inherent coherence of natural law. Understanding this balance gives a sense of perspective. Human timescales are fleeting compared to the steady ticking of neutron stars, yet the same physics governs both. The heartbeat of a living organism and the rotation of a pulsar are expressions of the same underlying order. One occurs in seconds, the other in milliseconds, but both demonstrate how the universe sustains motion through balance. In that sense, pulsars serve as a quiet reassurance that the cosmos is not random. Its vast machinery operates with precision that transcends chance. Every pulse recorded on Earth affirms that the structure of nature remains intact, that cause and effect, force and motion, continue to function without interruption. In the next segment, we will turn from the concept of order to the dimension of time itself. How pulsars allow scientists to study not just motion within time, but the very flow of time across the galaxy. Time is one of the most familiar concepts in daily life, yet one of the most difficult to define. It can be measured precisely, but its nature remains elusive. In physics, time is not a separate flow that moves through the universe. It is part of the structure of space-time itself, a dimension linked to motion and gravity. Pulsars, through their steady rhythm, provide one of the most direct ways to observe how time behaves across the cosmos. Each pulse from a neutron star marks an instant in that structure. Because pulsars rotate at stable rates, their signals trace the passing of time with extreme accuracy. When those signals are compared to one another, astronomers can determine how time progresses in different regions of the galaxy. If a gravitational wave passes through, it briefly alters the spacing of pulses, stretching or compressing the intervals. The changes are tiny, but measurable. Pulsars thus reveal that time is not perfectly uniform. It bends and flexes under the influence of gravity and motion. This property makes pulsars essential for studying cosmic timekeeping. They serve as reference points far beyond the reach of any clock on Earth. Each one runs according to its own rotation, unaffected by local conditions or mechanical decay. When hundreds of pulsars are monitored together, they define a timescale that belongs to the universe itself. This galactic network of ticking stars confirms that time can be measured consistently across vast distances, even though its flow is subtly shaped by gravity. The precision of pulsar timing also allows scientists to synchronize human-made systems with natural processes. For example, atomic clocks on Earth can drift slightly over long periods due to minute environmental effects. Pulsars, which exist in near-perfect isolation, do not. By aligning atomic time with pulsar signals, researchers can correct for those small deviations, maintaining long-term stability in global timekeeping systems. In this sense, pulsars extend the definition of universal time beyond the boundaries of Earth. The study of cosmic time through pulsars also provides insight into how the universe evolves. By observing how pulsars slow down, astronomers measure the rate at which energy dissipates into space. That slowing follows precise mathematical laws, linking the concept of time to the transfer of energy. A pulsar's spin-down acts as a kind of clock of age, revealing how long it has been since the parent star exploded. The rhythm of these stars tells the history of their creation, evolution, and eventual silence. Beyond science, pulsars invite reflection on the meaning of continuity. Their signals remind us that time is not something that passes around us, but something we are part of. Every rotation, every interval, marks an interaction between matter, energy, and the geometry of space-time. To observe a pulsar is to witness time expressed in motion, regular, measurable, and constant. It shows that the flow of time is woven into the structure of the universe itself, not a background against which events unfold, but a dimension that defines how events connect. The constancy of pulsars suggests that time, while affected by gravity, maintains coherence across the cosmos. This coherence makes science possible. It ensures that an experiment conducted here will yield the same results as one performed light years away. The pulses that reach Earth are not simply markers of distance. They are evidence that the laws governing time and motion remain intact across all of space. In a universe so vast that human lifetimes seem brief, pulsars provide a link to scales of time far beyond daily experience. Their steady beats continue for millions of years, offering a bridge between fleeting moments and cosmic ages. The rhythm they hold defines not only how we measure time, but how we understand our place within it. In the next segment, we will examine how these same principles of timing and stability are being used to explore another frontier. How pulsars can detect the presence of invisible matter that shapes galaxies, dark matter itself. The universe we can see, stars, planets, dust, and gas, represents only a small fraction of what exists. The rest is invisible, composed of something we cannot detect directly, dark matter. Its gravity shapes galaxies and bends light, yet it emits no radiation. Understanding this hidden mass is one of the central challenges in modern astrophysics. Surprisingly, pulsars, those dense, rotating remnants of ancient stars, may hold the clues that reveal how dark matter moves through space. Because pulsars act as precise cosmic clocks, even the smallest disturbance in their rhythm can be detected. If a cloud of dark matter were to pass between Earth and a pulsar, its gravity could slightly alter the arrival times of the pulses. These changes would be minute, but measurable with decades of continuous observation. In this way, pulsars become sensors not for light, but for gravity itself, sensitive to the invisible structures that fill the galaxy. Astronomers use large networks of pulsars, the same arrays that search for gravitational waves, to look for timing irregularities that might indicate dark matter. The principle is simple. If several pulsars show the same small deviation at the same time, the cause may be a common gravitational event. It could be a passing dark matter halo, a dense clump, or a stream of particles drifting through the Milky Way. Detecting such a pattern would allow scientists to map the distribution of dark matter without ever seeing it. Pulsars can also reveal how dark matter interacts with ordinary matter. Some theories predict that dark matter particles might accumulate inside neutron stars, changing their mass slightly or affecting their spin. Over long periods, this could cause a measurable difference in timing. So far, no such variations have been confirmed, but ongoing monitoring continues to narrow the possibilities. Each year of data improves the sensitivity, tightening the limits on what dark matter can be. These studies show how precision becomes a kind of vision. Where telescopes cannot see, timing can detect. The intervals between pulses carry information not only about the star itself, but about everything the signal has passed through. Space, once thought to be empty, reveals its hidden content through the smallest shifts in time. For astronomers, this work demands patience. The patterns they search for emerge only after years of consistent measurement. Each recorded pulse adds another data point to an expanding timeline, a record of the universe written not in light, but in intervals. The discipline mirrors the very rhythm they study, steady, deliberate, and calm. If you are listening now, that same calm can become your own. The universe, vast and filled with mystery, operates through laws that remain steady. Even what we cannot see follows order. Dark matter may be invisible, but its presence leaves traces in the predictable beats of pulsars, in the quiet evidence of timing itself. You do not need to solve those mysteries tonight. It is enough to know that they are being measured carefully, patiently, across light years of space. Let your thoughts align with that rhythm for a moment. The regular turning of stars, the invisible forces balanced in silence. Just as astronomers trust the stability of those distant signals, you can trust the stability of your own world for now. If sleep has not arrived, let it come gradually, in the same unhurried way that pulsars reveal their secrets. The universe keeps time, you only need to rest within it. Astronomy often begins with light, but in many cases, silence speaks just as clearly. The universe is full of signals, radio waves, X-rays, and faint glimmers of distant galaxies, but it is also full of quiet. For scientists studying pulsars, that quiet is not emptiness. It is part of the data. The pauses between pulses, the sudden absences, and the faint changes in rhythm all contain information about the environment around a neutron star. Silence, in this sense, is another way the universe communicates. Each pulsar has a rhythm shaped by its rotation and magnetic field, yet even the most consistent among them can fall briefly silent. Some pulsars stop emitting detectable radio waves for seconds, minutes, or even days before resuming. These objects are known as intermittent pulsars. Their temporary quiet periods may be caused by shifts in magnetic alignment or changes in the flow of charged particles around the star. When emission resumes, it is as regular as before. The silence, therefore, is not a breakdown but a transition, an adjustment in how energy escapes from the star's magnetic poles. For astronomers, these interruptions provide valuable clues about the physics of magnetospheres, the regions around pulsars where electromagnetic forces dominate. During silent intervals, the electric currents and plasma near the star may rearrange, resetting the system. When the pulses return, their properties, strength, polarization, or timing often change slightly. By studying these variations, scientists learn how pulsars regulate themselves, how matter and magnetism interact under conditions that cannot be reproduced on Earth. Silence also reveals distance and density. When a pulse passes through interstellar gas, some of its energy scatters or fades. In areas where the gas is dense, the signal weakens or vanishes temporarily. Recording when and where these disappearances occur helps map the structure of the space between stars. The absence of a signal becomes a measurement in itself, a record of matter too thin to see but too influential to ignore. Beyond the physical, there is something quietly profound about how science treats silence as data. In most human experiences, silence feels like nothingness, an absence of meaning. In astronomy, it is the opposite. The universe's quiet moments tell us what is hidden, what lies between. Pulsars make this visible. Their steady beats outline spaces of stillness, and those spaces, when measured carefully, describe the structure of the cosmos. The same principle applies to the instruments that detect them. A radio telescope pointed at the sky records both presence and absence. Its receivers do not know which is more significant until patterns emerge. What appears empty at first can later reveal a cycle or change that transforms understanding. Discovery, in many cases, begins in apparent silence. For listeners on Earth, the concept carries an echo of its own. The universe functions through contrasts, sound and quiet, light and darkness, motion and stillness. Pulsars show that silence is not the opposite of activity but part of its rhythm. Between pulses, the star is not inactive, it is continuing its rotation, building toward the next signal. The pause completes the pattern. This idea applies to observation, and it applies to life. Progress and rest, action and stillness, each gains meaning from the other. In the same way, the universe measures both the presence of light and the spaces between. Pulsars remind us that stillness, too, can hold information, value, and balance. The absence of a sound can reveal just as much as the sound itself. In the next segment, we will turn from silence to the passage of time once more, exploring how pulsars and their gradual slowing help scientists understand the future evolution of stars and galaxies. Every pulsar begins with power and precision. At birth, it spins hundreds of times per second, driven by the energy released in a supernova. Over time, that rotation slows. The pulses that once came in rapid succession begin to stretch farther apart. To the human eye, the change is imperceptible, but across thousands or millions of years, it transforms the pulsar from a bright, fast beacon into a quiet, aging star. This gradual slowing is the natural outcome of energy loss, an inevitable consequence of physics. The rate of slowdown depends on a pulsar's magnetic field and its initial speed. Stronger magnetic fields radiate more energy, causing faster deceleration. Weaker fields allow a slower decline. Each pulsar follows its own path, but the general pattern is the same. The loss of rotational energy is steady and measurable. As the spin decreases, the radiation weakens, and eventually the beam becomes too faint to detect. The star does not disappear. It simply crosses what astronomers call the death line, a threshold below which the conditions for producing radio waves no longer exist. Even in this quiet phase, the neutron star remains a remarkable object. Its density, structure, and magnetic field persist long after its signals fade. In some cases, it may still emit X-rays or gamma rays from residual heat. In others, it drifts through space as a cold, dark remnant, an almost perfect sphere of neutrons, invisible but enduring. These silent neutron stars outnumber active pulsars, forming a hidden population that traces the full life cycle of stellar evolution. By studying the distribution of active and inactive pulsars, astronomers can estimate how often massive stars explode in our galaxy. Every pulsar was once a supernova. Their ages and spatial distribution form a record of star formation over millions of years. The slowing of their rotation provides a cosmic clock for this process. By measuring how quickly pulsars fade, scientists can reconstruct the rhythm of stellar death and rebirth in the Milky Way. The end of a pulsar's active life does not mark an ending for the universe itself. It is part of a cycle. The elements expelled in its original explosion become part of new stars and planets. Over cosmic time, even those will evolve, collapse, and renew the process. Pulsars remind us that change is constant but predictable. The slowing of their spin is a quiet signal of stability. The same physical laws that began their rotation continue to guide their decline. For researchers, the fading of pulsars presents both a challenge and an opportunity. As older pulsars become too weak to detect, new generations of telescopes with greater sensitivity are designed to find them. Each discovery adds to the understanding of how energy transforms over time. Mapping pulsars at different ages gives scientists a view of the galaxy's long-term evolution, its aging stars, its cooling gas, and the steady shift from youth to maturity. In a much broader sense, the story of pulsars reflects the story of the universe itself. Everything that begins in motion eventually slows. Energy spreads, systems cool, and activity gives way to quiet balance. Yet in that slowing, structure remains. The cosmos does not collapse into chaos. It continues to evolve according to patterns that endure. Pulsars make that truth visible, or rather, audible, in their fading rhythm. Each one is a voice that gradually softens but never loses its order. In the next segment, we will turn to the human side of this cosmic narrative, how these silent clocks have changed our view of existence, and why their persistence mirrors our search for meaning within an ever-changing universe. For most of human history, the night sky was a mystery of lights, steady, timeless, and seemingly unchanging. Stars appeared eternal, fixed points marking the passage of days and seasons. The discovery of pulsars transformed that view. They revealed that even the most stable lights in the sky are dynamic. Each pulse is a reminder that the universe is not frozen in place but alive with motion, energy, and transformation. Through pulsars, humanity learned that constancy and change coexist. When Jocelyn Bell Burnell first detected that faint, repeating signal, she could not have known it would reshape how we think about permanence. The pulses she recorded were not artificial or accidental. They were natural, self-sustaining rhythms of dying stars. That realization carried both scientific and philosophical weight. It showed that precision and order are not inventions of the human mind. They are built into the fabric of reality itself. The universe does not require our observation to be stable, it simply is. Pulsars speak to the balance between fragility and endurance. Each one began in chaos, formed from a collapsing star that should have scattered its matter forever. Instead, it condensed into a form so dense and ordered that it became a clock, measuring its own existence with unwavering precision. The same process that destroys also creates structure. This duality, decay turning into rhythm, echoes across scales, from cosmic to personal. It reflects how order can emerge from disruption, how systems can find harmony after collapse. The regularity of pulsars also carries an emotional resonance. Their distant, mechanical precision reminds us that nature does not act out of will or intention. Yet, paradoxically, that impersonal order creates meaning. The fact that these objects continue to turn, perfectly on schedule, long after the stars that birthed them have faded, reminds us that existence itself has continuity. The forces that govern matter are impartial, but they produce beauty in their consistency. For scientists, pulsars symbolize the triumph of observation and patience. They are difficult to find, harder to interpret, and impossible to manipulate. To understand them requires years of careful listening. That commitment mirrors the persistence of the stars themselves. In their data, researchers find not just numbers, but a sense of connection to something vast and reliable. The same physical laws that keep pulsars spinning also bind galaxies, govern atoms, and shape human life. This recognition brings humility. The precision that feels extraordinary to us is ordinary to the cosmos. A neutron star spinning hundreds of times per second does not strive for accuracy, it simply follows the path laid out by physics. The perfection we observe is not deliberate but inevitable. That realization can be both grounding and comforting. It means that order is not fragile. It is woven into the universe itself. For those who study them, pulsars represent continuity without intention, stability without design. Their existence suggests that meaning does not depend on control or creation but can arise from understanding. To observe them is to glimpse the underlying rhythm that connects all matter and motion. Each pulse that reaches Earth is an echo from deep time, a reminder that the same principles shaping the stars also operate within us. Science often reveals truths that are larger than their immediate discoveries. The study of pulsars has done more than confirm theories or measure time. It has expanded our idea of what order means. The universe does not seek harmony, yet it produces it. The stars do not strive to endure, yet they leave behind patterns that last for millions of years. Pulsars show that stability and change are not opposites, but partners in a continuous cycle of transformation. In the next segment, we will explore how this cosmic rhythm resonates on a human level, how the steady rotation of distant neutron stars mirrors the cycles of life, energy, and rest that shape our own existence. The universe operates in patterns, and so does life. From the spin of the Earth to the beat of a human heart, rhythm underlies every system. Energy moves in cycles, rising, transforming, and returning, and those cycles maintain order across scales. Pulsars, rotating with constant precision, are distant expressions of the same principle that keeps oceans moving, seasons turning, and living organisms in balance. They are reminders that nature's language is repetition with variation, stability shaped by motion. On Earth, many processes follow predictable rhythms. The day begins with light, ends with darkness, and repeats. Tides rise and fall under the pull of the moon's gravity. Plants open and close their leaves with the sun's passage. Even at the molecular level, life depends on oscillation. Cells divide, neurons fire, hearts contract and relax. Every rhythm is a form of timing, a measure of energy flowing through a system. Without those cycles, life could not sustain itself. Pulsars show that such timing is not unique to biology. It is a property of physics itself. Their rotation is a vast echo of the same principle, the conversion of stored energy into motion, and motion back into equilibrium. The forces that shape a neutron star's spin are the same that keep planets orbiting, winds circulating, and ecosystems stable. Across all scales, the universe conserves balance through regularity. Understanding this connection helps explain why rhythm feels natural to us. Human bodies evolved within an environment ruled by cycles. Our internal clocks synchronize with the world's patterns, sleep and wake, activity and rest. When the brain senses a steady rhythm, whether in sound, light, or heartbeat, it aligns with it. The predictability brings calm because it mirrors the stability found in physical systems. This is why repetition is comforting, why rhythm in music or nature eases tension. It reflects a universal order that the body recognizes instinctively. Energy, too, follows cycles of release and renewal. A pulsar converts rotational energy into radiation, gradually slowing but never losing the structure that defines it. On Earth, energy from the sun drives growth, is consumed, transformed, and then recycled. No process continues indefinitely, yet none is lost. Change and continuity coexist. Pulsars express that balance over cosmic timescales. Life mirrors it on biological ones. When scientists study these patterns, they are observing the same law in different forms. Conservation, energy, and motion persist, though their expressions shift. In this way, pulsars are not foreign objects but distant extensions of familiar processes. Their steady turning is another version of what happens in every system that finds balance between input and output, between creation and decay. Recognizing these connections deepens the sense of unity between humanity and the cosmos. The rhythm of a pulsar is extreme, fractions of a second measured across light years, but the logic behind it is universal. Both the cell and the star follow the same equations of motion and conservation. Both depend on repetition to exist. The difference is only scale and duration. This awareness transforms the perception of the universe from something distant into something continuous with ourselves. The same cycles that govern stars govern hearts, seasons, and minds. Order is not imposed from above, it arises naturally from the properties of matter and energy. To observe a pulsar is to see a principle of life itself, reliability built from change, renewal through motion, calm within repetition. In the next segment, we will return once more to the personal perspective, connecting the rhythm of pulsars and life cycles to rest, renewal, and the way science helps us find peace within an ever-moving universe. In every system, rest is part of the rhythm. Stars, cells, and people all follow cycles of activity and quiet. Even pulsars, though they seem endlessly in motion, have phases of calm. Their light can fade for a time, their rotation slow, their signals weaken, yet none of this marks an end. It is renewal through stillness. The energy that once burst outward becomes balance. What begins in intensity settles into continuity. Nature has no permanent rest, but it has steady recovery, woven into the structure of everything that exists. The same principle applies to life on Earth. Every organism depends on periods of pause to restore its systems. Sleep, for example, is not an interruption but a function. It allows the body to regulate energy, repair cells, and reset the mind. During sleep, the brain reorganizes memory and emotion, processing what was experienced in wakefulness. This rhythm, wake and rest, activity and quiet, is a biological reflection of the same pattern that governs the cosmos. Thinking of rest in this way changes how we see it. Sleep is not a withdrawal from life, but a return to equilibrium. Just as pulsars continue to spin even during their quiet phases, we too remain active in unseen ways. Our bodies adjust, balance, and realign. The calm we feel as we fall asleep mirrors the calm of a system finding order after motion. The physics of restoration and the biology of rest are linked by the same logic. Stability through rhythm. When scientists observe pulsars, they are watching energy manage itself with precision. The star releases just enough radiation to maintain equilibrium, never too much, never too little. In our own lives, rest performs a similar task. It balances the energy we expend in thought, movement, and emotion. Without rest, systems drift from order into noise. With it, they regain structure. Sleep is therefore not the absence of activity, but the condition that allows activity to continue with purpose. If you are listening now, you can let that idea become part of your own rhythm. The universe is full of motion, yet every motion includes its pause. The steady pulse of distant neutron stars, turning in perfect rhythm, reminds us that even the most powerful forces alternate between release and recovery. There is time for movement and time for stillness. Both are essential to balance. Let your breathing follow that pattern for a moment. Each inhale is motion, each exhale a return to calm. The space between them, the pause where nothing is forced, is where renewal begins. You do not have to chase sleep or hold on to wakefulness. Like the cycles of stars, it will come naturally when balance restores itself. The regularity of pulsars proves that systems can sustain harmony even after great energy is spent. Their persistence is a quiet assurance that rest does not mean decline. It means continuity under new conditions. When you drift into sleep, your own system follows that same universal rule. Energy reorganizing, rhythm resetting, order returning. If rest is close, allow it to arrive in its own time. The same physics that keeps the stars turning governs the calm in your body now. The pulse of the universe continues, steady and constant, and you are part of that rhythm. In the end, every rhythm slows. Even the universe, in its vastness, follows patterns of rise and decline. Stars burn through their fuel, galaxies drift apart, and energy spreads thinner over time. Yet within this long unwinding, there is remarkable order. Pulsars stand as proof of that continuity, remnants of death that became instruments of precision. Their rotation is not eternal, but it endures far beyond imagination, a balance between loss and persistence that defines the cosmos itself. Each pulse that reaches Earth began as the aftermath of destruction. What was once a massive, burning star collapsed into a point of immense density and order. Out of chaos came stability. Out of explosion came rhythm. The regular signals that astronomers record today began as echoes of that transformation, traveling for thousands of years before touching our instruments. In their repetition lies a simple truth. Energy does not vanish, it reorganizes. Motion continues, structure remains. Pulsars remind us that time, no matter how vast, is measurable. Their pulses mark seconds across centuries, tracing the fabric of the universe with unwavering precision. They prove that even at cosmic scales, order emerges naturally, requiring no intervention. Matter follows the same laws everywhere, from the smallest particle to the largest galaxy. This universality binds everything together, forming a quiet continuity between what we can see and what lies beyond. For humanity, that understanding brings perspective. We often view change as loss, but in physics, change is only transformation. The slowing of a pulsar is not failure, it is the fulfillment of its nature. The same principle applies to all systems, from stars to living beings. Energy shifts, structures evolve, and balance returns in new forms. Nothing remains the same, yet nothing is truly gone. The universe conserves, converts, and continues. To observe pulsars is to glimpse endurance without intent. Their constancy is not chosen, yet it persists with clarity and grace. The precision that defines them is a reflection of the universe's own equilibrium. Each pulse is a moment of order against the background of expansion, a small but enduring reminder that harmony exists even within entropy. In their silence, too, there is meaning, a kind of peace that follows every act of creation. The same calm extends to us. Just as the universe finds rhythm through motion, we find it through breath, through thought, through sleep. Rest is the personal form of cosmic order, a return to equilibrium after motion. When you sleep, you take part in the same pattern that governs stars, energy reorganizing, systems finding balance, time continuing without interruption. The rhythm that guides pulsars also guides you, scaled down to the quiet pulse of a human life. The story of pulsars, then, is not just about distant stars. It is about continuity itself. It shows that order can arise from collapse, that rhythm endures beyond chaos, and that every cycle, no matter how immense, contains moments of peace. These cosmic clocks keep time not only for astronomers, but for anyone who finds reassurance in the persistence of natural law. They are the heartbeat of the universe, slow, steady, and constant. So tonight, as you rest, remember that far beyond the sky, those clocks are still turning. Their light may never reach your eyes, but their rhythm shapes the structure of time itself. In their motion, the universe keeps its balance, and within that balance, so can you. We from Sleepy Stories wish you a good night.